All right, let's get right into it. For decades now, engineers have been on this incredible quest to perfectly recreate one of the most intense, most complex manufacturing processes there is, welding. And to do it all inside a computer. So today, we're going to trace that entire journey, from a really simple idea on paper to what's now a nearly perfect digital copy of reality. And this quote from the engineer R.A.S. Shaholsky, it just nails why this whole quest is so important. See, the factory floor, the production shop, it's not some university lab where you can just mess around and try stuff out. No way. Mistakes out there cost millions, they waste tons of material, and honestly, they can be super dangerous. The stakes are just way too high for guesswork. And that really gets to the core of the problem, what you could call the hit or miss problem. I mean, think about it. Welding literally holds our world together. We're talking skyscrapers, cars, probably the phone in your hand. But getting that weld right, well, that's a whole other story. What we're dealing with here is melting and fusing solid metal in just fractions of a second. The physics involved are so incredibly complex that the tiniest, most subtle change in temperature and speed in anything can be the difference between a perfect, strong bond and a complete, catastrophic failure. You have to get it right every single time. So that's the big challenge, right? If you can't just experiment on the real thing on the factory floor, how do you get better? How do you innovate? How are you supposed to push the limits to make things stronger or lighter or safer? Well, you need a totally new kind of laboratory. And that new lab, it wasn't built with bricks and mortar. The answer, of course, was to build the whole thing inside a computer. The big idea was to take the entire messy, hot, physical process of manufacturing and just turn it into clean, predictable data you can see on a screen. Now, I know this diagram looks a little complicated, but the really cool part is where weld simulation fits in. See, design up at the top and manufacturing way down at the bottom. Simulation is that critical bridge connecting them, right there in the middle. It's almost like a crystal ball. It lets engineers see the future, to see the real-world effects of their design choices before a single piece of metal is ever even touched. And this brings us to the ultimate goal of all of this work, and that's creating something called a digital twin. Now, this isn't just a drawing or some simple 3D model. Oh no, it is a living, breathing, virtual copy that is designed to behave exactly like its real-world counterpart. The dream here is to test it, to break it, to perfect the digital version so that when you go to build the physical one, it's flawless right from the start. But, getting to that perfect digital twin, that was a long road. The journey actually started decades ago with the very first attempts to model the most basic part of any weld, the heat itself. And just look at this timeline for a second. This was not some overnight breakthrough. We're going from a purely theoretical model back in the 1930s to the first ever 2D computer models in the 70s, using a technique called finite element analysis, which is basically just a super clever way to break a huge, complex problem into thousands of tiny solvable little pieces. All the way to 1986 before computers were even powerful enough to try doing a full 3D simulation. The first really big idea, the Rosenthal model, was just beautiful in its simplicity. It basically said, hey, what if we just pretend the welding arc is a single moving point of infinite heat? It was a massive oversimplification for sure, but it was a start. It was a way to finally begin applying real math to this incredibly chaotic process. And yeah, it was a brilliant start, but it immediately makes you wonder, right? Is that really what a welding arc is like? Is it just one tiny, infinitely hot dot zipping across the metal? The answer, as scientists pretty quickly figured out, was not really. And that realization, well, that's what sparked the next great leap forward in simulation. To get closer to reality, they had to move beyond the simple idea of a single point and really think about how heat actually spreads out. Okay, so here's the big conceptual shift. The heat from a weld isn't all concentrated at one single point. It's distributed. It spreads across a surface and down into the volume of the metal itself. So the new challenge became, okay, how do we mathematically describe that distribution? And this illustrates that evolution perfectly. On the left, you've got the early disk model, where the heat is just spread across a flat 2D circle on the surface. But then look at the right. That's the hemisphere model. This was a huge step forward because it finally started to account for the digging action of the arc, modeling the heat as a 3D volume that actually penetrates into the metal. So how'd they do it? How did they model this? Well, they used a concept you probably remember from math class, the Gaussian distribution, better known as the classic bell curve. And it was the perfect tool for the job. It describes something that's most intense right at the center and then gradually fades out toward the edges, which is a pretty great description of the heat from a welding arc. Let's look at a real example. Now, don't worry about the equations here. Just focus on the graph on the left. This shows the heat distribution for a laser weld. See that really sharp, narrow peak? That's a super high-intensity heat source, all concentrated in a tiny little area. The bell curve is tall and skinny. Now, compare that with the graph on the right. This is for a submerged arc weld. The bell curve here is wide and low, kind of like a gentle hill. It's the same total amount of energy, but here it's distributed over a much wider area with a lower peak temperature. Using these Gaussian models was what finally allowed scientists to account for these really crucial differences. So this brought the simulations incredibly close to what happens in the real world. But there was still one nagging little problem that was keeping that digital twin from being a perfect mirror of reality. Here's the thing, a weld isn't stationary, right? It's moving. And that motion makes the little molten pool of metal lopsided. It's asymmetrical. Think about it for a second. The temperature gradient right at the front of that moving weld is incredibly steep, while the pool behind it cools down more slowly, which creates a longer, more gentle tail. A simple symmetrical hemisphere just couldn't capture that shape. So the solution was another stroke of genius, the double ellipsoid model. Instead of using one symmetrical shape, researchers cleverly combined two different halves of an ellipsoid. They used one steep half for the front of the weld and a different, longer half for the trailing rear. And that was the trick that finally allowed the simulation to accurately model the true asymmetrical shape of the moving weld pool. And that innovation right there was the final key. Today, the double ellipsoid model is the #1 most popular, most flexible, and most accurate model used in the entire industry for predicting what's happening with the temperature inside a real-world weld. So, why does any of this matter? What's the big deal? Well, because perfecting this digital twin unlocks everything you see here. It lets us innovate faster to invent and test brand new alloys completely on a computer. It helps us design stronger and lighter parts for our cars and airplanes, which makes them safer. It reduces waste in our factories, saves money, and just builds a safer, more efficient world for all of us. It's a really powerful idea when you stop and think about it. This decades-long, painstaking quest to simulate a single weld has ended up giving us a tool to basically predict the future. And it kind of leaves you wondering, doesn't it? As these digital twins get better and better, until they're truly indistinguishable from the real thing, what other impossibly complex problems are we going to be able to solve next?